Welcome to the Mentors Workshop. Think of this explainer as your absolute first day as a new apprentice. We're about to embark on a seriously exciting journey into the hidden underlying mechanics of software. We're going to look right past the shiny graphical interfaces and the colorful buttons, and we're going to dig straight into the actual engine of the programs we use every single day. You know, Elliot Tchaikovsky once said something that really hits the nail on the head here. He said it's amazing and honestly rather disconcerting to realize just how much software we run without knowing for sure what it does. And think about it. Every day we're downloading updates, installing apps, clicking agree, and interacting with these digital black boxes. We basically just blindly trust that the code is doing exactly what it claims to be doing. But what if you actually had the power to pry open that black box and look inside? Well, that's exactly the superpower we're unlocking today. All right, let's jump straight into Section 1, The Art of Discovery. It is time to peek inside the black box. To guide our investigation today, we'll be pulling techniques straight from Eldad Ilam's foundational text, Reversing Secrets of Reverse Engineering. Now, I want to be clear right off the bat. We aren't going to treat reverse engineering like some dry, tedious technical chore. No way. Instead, we're approaching this as a thrilling process of discovery. It's about puzzle solving and code breaking. It's essentially recovering the design blueprints of a program when the original instructions are just completely missing. But before I hand over the tools, we really need to talk about intent. Think about the stethoscope analogy for a second. Reverse engineering is a completely neutral tool, much like a stethoscope. Now, a burglar could use a stethoscope to listen to the tumblers of a safe clicking into place during a bank heist, right? But that exact same tool is used by a doctor to detect a heart murmur and heal a patient. The tool itself isn't inherently good or bad. It is literally all about how you choose to use it. So what are the ground rules for us here in the workshop? Well, we operate within strict ethical boundaries. We reverse engineer to achieve interoperability, which just means making sure different software systems can actually talk to each other. We do it to conduct critical security research and create signatures for malware detection. We do it to evaluate the true quality and robustness of third-party software before we ever trust it on mission-critical systems. And we do it to discover unexpected flaws before they cause massive system failures. In short, we are the doctors in that stethoscope analogy. Moving right along to Section 2, the language of machines. Before we can start swinging our tools around, we absolutely have to understand how computers think and what materials we're actually working with. Let's think about the journey of code. As developers, we normally write in high-level, human-readable languages, think C++ or Java. But here's the catch. A computer's central processing unit, the CPU, has absolutely no idea what to do with that text. It needs a translator. And that translator is called a compiler. The compiler takes all our nice high-level logic and just crushes it down into a stream of ones and zeros called machine code or object code. The huge problem for us? Once the compiler does its job, it completely strips away all that nice human-readable context. Because we can't exactly sit there reading a giant wall of ones and zeros, we rely on assembly language. This is absolutely foundational for reverse engineering. It is simply a human-readable textual representation of those binary instructions. So instead of staring at a cryptic hex code, we get to see a command word like move for move or add for add. It is quite literally the closest we can possibly get to reading pure machine logic. And to really grasp that machine logic, you also need to understand its environment. Enter virtual memory. This is a clever operating system mechanism that gives applications their own isolated, contiguous memory space. As we're investigating a binary, we really need to know how the operating system is organizing the data structures, the variables, and the code itself within this virtual space. Think of it as the playground where all the actual execution happens. Okay, let's gear up. Section 3, your reversing toolkit. Welcome to the workshop's armory. It's time to introduce the primary instruments we're going to use to crack open these binaries. First step on the bench is the disassembler. Think of this as your master translation device. A disassembler takes that compiled executable file, that super cryptic stream of numbers we talked about, and automatically decodes it back into the readable assembly language text. It reads the object code and generates a textual map, which lets us see the exact step-by-step instructions the CPU is being asked to perform. Our second major tool? The debugger. Honestly, a debugger is like having a superpower that lets you freeze time. It allows you to observe a program while it's actively running. You can set what are called breakpoints to pause the software at an exact specific moment. And from there, you can step through the code line by line, inspecting the live memory, the registers, and the overall state of the program as it breathes. Now, these two tools give us our two primary methodologies of analysis. Offline code analysis, which is sometimes called deadlisting, heavily relies on your disassembler. It's basically like reading a static blueprint. You're mapping out the program structure without ever actually running it. On the flip side, live code analysis relies on your debugger. Here, you are actively running the code to observe the data flow and see exactly how variables change in real time. It's exactly like watching a car engine run with the hood wide open, so you can see every single moving part. Just to give you a quick visual of your future workspace. In an offline environment, say mapping out .NET code, you're statically analyzing the structural hierarchy in the text instructions. But jump over to a live debugging session, and it's a whole different vibe. You're watching live memory dumps and active command terminals. You still see the assembly code right there in the main window, but everything around it is reacting and updating to the live environment. All right, Section 4, a simple investigation. Consider this your first day on the job. Let's walk through the mental approach you take in an actual simulation. If I can give you one massive piece of advice for your first day, it's this. Don't obsess over memorizing hex codes. Instead, focus entirely on your mindset. Reverse engineering is heavily dependent on puzzle solving, deep curiosity, and logical deduction. Remember, your tools only present the raw information. They are never just going to hand you the final answer. It is always up to you, the human mind, to logically deduce the actual meaning behind the machine's behavior. So how do we actually deduce that behavior? Well, we deconstruct the machine logic piece by piece. We watch the CPU interact with registers. These are small, ridiculously fast storage spaces right on the CPU itself, like the EAX register, that hold immediate data. Then, we watch the code test that data to set flags. Think of flags as tiny indicators of specific conditions. For example, if a program tests a variable and finds out it equals 0, boom, it sets the 0 flag. And finally, we hunt for conditional branches. Based on whether that 0 flag is set or not, the program literally makes a decision to jump down one path of code or another. By tracing those registers, flags, and branches, we can map out the entire brain of the program. And that brings us to our final stop, Section 5, hunting for hidden threats. This is where the rubber meets the road, applying our craft to actually secure the system and protect users globally. When it's time to really hunt for serious threats, we bring out the heavy artillery, deep kernel-level debuggers like WinDb. See, user mode debuggers just attach to a single app, like your calculator or notepad. But a kernel mode debugger, it sits right down alongside the absolute core of the operating system itself. It gives security researchers an unlimited, godlike view of absolutely everything happening on the system. It is literally the ultimate vantage point for monitoring stealthy, malicious, system-wide activity. And here's why having that ultimate vantage point is absolutely crucial. By analyzing binary code at this deep level, we can unmask some profound threats. We can dissect highly complex malicious software and stealthy viruses to figure out the exact mechanisms they use to infect a host. We can identify and patch hidden backdoors long before they can be exploited by bad actors. We can even uncover undocumented code that developers might have accidentally or intentionally left behind. Ultimately, doing all of this allows us to extract recognizable patterns from that nasty code. We use those patterns to create the exact signatures that antivirus scanners use to protect billions of devices every single day. So there you have it. You now know how computers think, you've taken a tour of the armory, and you understand the mindset required to do this work. The black boxes are officially ready to be opened. The tools are in your hands. The only question left is, what secrets are you going to uncover?